All right, welcome again. We're going to close the poll now and get started. There's going to be another question a little bit later. Welcome to How Your Private Well Works. This is part of the private well class. It's sponsored and supported by the Rural Community Assistance Partnership and US EPA, who funded this. We're at the Illinois State Water Survey and Illinois Water Resources Center at the University of Illinois, we'll get started. Okay, today's topics. First, we'll talk about what is a private well class. There's several parts to it. Then we'll go over what's being covered in our webinar, go through some logistics about using GoToWebinar, the service that we're using, so that you can ask questions if you need to, and how this will all work. And then we'll go through the material for today and sum things up. And then at the end, we think this will be about 45 minutes of 40 to 45 minutes or so of a presentation, and then the rest of the time is for questions. And the real idea behind this is so that it gives you an opportunity to ask questions today. Okay, so first off, the private well class, it's a series of 10 lessons that are sent via email over 10 weeks, one a week. It started last Wednesday. If anybody signed up for the class itself, after that, it'll start that day, and you'll get one a week, 7 days later for each one. There are also 3 webinars. This is obviously the first of those 3 that are meant to support the lessons and give all the participants a chance to ask questions. And there's also the website where you signed up. That website isn't very robust to date, but as we move forward and add the lessons and find additional resources and materials, everything will be put there. So if we find a great video on how to do a certain thing to clean out your well, or the proper way to sample from a spigot or whatever, we'll add all that kind of information, and in the end, the web pages for each lesson will actually have more information than the lessons that were sent to you directly. So, that page should stay live in theory in perpetuity, so that you can always go back and find resources that way. Excuse me. This is the website. All of you probably have been here to, anyone that registered for the webinar came to here. Again, it's sponsored through the U of I, the Water Survey and Water Resources Center, by RCAP and the US EPA. So one of the questions, we've had a number of emails asking about this webinar in reference to it being the class itself. And maybe we didn't make that clear enough on the web page, but the class lessons are actually emailed. So if you are on the webinar thinking this is the class, it's really not. There is a place to sign up on the website for the class materials. And again, today and the other 2 webinars that we'll be hosting are meant to support those 10 lessons. And that's not to worry. The way this is set up, you can start the class anytime. If you don't start the class till April, you'll still get 10 weeks in a row. You'll get a email from us that has those 10 lessons. Okay, so to enroll, if you go to the website, you can click on the How It Works tab, and it explains it there, and then click on here, click here to enroll for free, or you can click on the Enroll in Class tab, and either one will take you to this page where you can sign up, and we just need an email address, and we're asking for your first name and the state you live in, and that helps us to show EPA that we're reaching the whole country, for one thing, and also gives us an idea of how our partners are doing and where folks have a need and that sort of thing. Once you click sign up, you'll receive a welcome message, and then the first lesson and a pretest, and then the next will show up a week later, as I mentioned. Okay, so the 10 lessons, the first one, I'm just going to go through what's in each one so that everyone's clear. And this just started last Wednesday for anyone who had registered before the 9th. The first is called The Science of Groundwater. It's a geology lesson on what an aquifer is and some of those materials, which we'll go through a little bit today. The second one, which should go out today, this afternoon, for anyone who was registered before the 9th, is about groundwater flow to your well and how flow and aquifer flow and water flow can cause well contamination. The third is well construction and well types and those related issues. The fourth is well infrastructure, so it's more about your pump and your pressure tank and your pitless adapter and the things going in your house and kind of the engineering behind your well. Excuse me. 5 is well O&M and best practices, so the things you need to do to maintain your well, what best practices you should follow, and there's a number of those if you really want to be a good steward of your well and try to make it last as long as you can and keep your equipment the way it should be. The others 5 lessons as we move forward. Lesson 6 is on emergencies, failures, and problem solving. So things like what happens when your well goes dry, there's a flooding event, some other kind of failure, and things that you can do to try to problem solve those issues. So 7 is getting help finding local answers. You'll notice as you take this class, we stress that a lot, the finding local answers. We're in Illinois, and we certainly, at the water survey where I work, we certainly have helped well owners with their issues for 100 years. But we don't know necessarily the best answer for questions in other parts of the country. And really the best help you can get is locally from your local health department or co-op extension or your Department of Natural Resources or your geological survey. Those folks know your area, know what your water quality issues are, know what your geologic issues are, and they're the ones that you really need to lean on. And we'll try to, in this lesson, actually get to some of the nuts and bolts of who you can contact to find some of those answers about your well. And I apologize, I'm losing my voice a little bit, but hopefully we'll get through today. Lesson 8 will be about groundwater, source water, and wellhead protection. A little bit of that was touched on in the lesson that comes out today, but really it was about sources. And in 8 we'll talk about setbacks and what things you can do to try to make sure that your well and the aquifer you're using for your water supply are protected from any kind of contamination. 9 is how to sample your well and sampling issues and interpreting those results. There's a lot of good information out there, and again, a lot of times that comes down to local issues. Local lab you use may have their own requirements, some of those things, and but we'll give you some good resources to use to get you started. And lastly, water quality issues and treatment solutions. So basically, if you do get things in your well, or you do have some kind of contaminant in your well, whether it's natural or anthropogenic and caused by something that's going on around you, what that means and what kind of treatment solutions that might be out there. All right, moving on. The other part of this class are these 3 webinars, and so those are the 3 listed on the website. Now we plan to do these 3 webinars multiple times, and the other dates haven't been decided yet, but we'll do this webinar again, and as we move through this, this being the first time we've given it, we'll get some questions today that we maybe probably should have included some of those issues in this webinar. It might improve a little bit for the next time, but the idea being that through these 3 webinars we'll provide a little additional information that go along with the lessons. And so today's lesson is really about how your well works and water gets into your well. The next one is about taking care of your well maintenance and the things you can do, and the last one is about the water quality in your well, treatment issues and taking samples and all those things. And so, as I said, we plan to repeat these at least 2 more times live, and we also hope to do one of those in the evening for folks that aren't able to attend this during the day. So about today's webinar, we're recording this so that it will be available on YouTube and on the website. I got a number of emails this morning from people saying, hey, my plans have changed, I can't be here today. And again, as I mentioned, we'll be repeating these live at least 2 more times. And as far as the questions, I think we've really got that handled already, but we did have 450 people sign up for today, which was a pleasant surprise. And so we're asking that, one, you try to keep your questions to the material that we're covering today, The other issues can be covered in later webinars, and we also ask that you use the question box. You may have noticed, I turned my email off for this so that we're not having emails pop up all the time while we're doing the webinar. So there's 3 of us here where we're going to write down every question. We'll try to get to all those. We're not sure. This is the first time we've done this. How many we might want to be able to answer, but eventually we'll develop a frequently asked questions section on our website, and we'll answer all those questions. And one thing I'd like to say about this, I'm a groundwater hydrologist, and there's certain aspects of this class that I'm much more knowledgeable about than others. But at the Water Survey and at some of the other agencies around the state and country, we've made a lot of contacts already with folks who we will lean on to help answer some of the questions you have. So I may not be able to answer them today, but we will get answers to your questions and try to provide some assistance. So are there anything I need to do before I move forward? Okay. All right. Here's the webinar window. If you, when you sign up for GoToWebinar, there's that long bar on the right side. If you have a question section and the minus sign that's showing on the screen is actually a plus, then it's minimized. If you click on it, this is where you can ask your question. Most of you already figured that out whenever you said hi earlier, which is great. And so I just want to make sure everyone understands where they should be asking questions today. With this many people, we really couldn't open up the mics, or it would be quite a challenge, I imagine. Okay, so going on to groundwater basics. Water in the ground is stored in the spaces between the geologic materials, whether it be sand or bedrock, sandstone or gravel, and so it's a porous system, and how much water is stored in an aquifer is based on how much pore space there is. So when we talk about porosity, that's one of the key characteristics of an aquifer. It's the volume of pore space versus the total volume. So the way I explain this most of the time is if you have an aquifer that's, say it's a sand and gravel aquifer that's 100 feet thick, and the porosity is 30%, that means if you could separate all the pore space from the actual sand grains, you'd have 30 feet of water at that location. And so, the porosity matters. If you're in a crystalline bedrock aquifer where you're in a low-yielding well, the porosity over a large chunk of the area may only be 1 or 2%, because the only place that water can be stored is in the fractures between the sections of rock. And so one of the measures of how much water can be stored and how, quote, good an aquifer are is a measure of its porosity. And so this is from Arizona's Well Owner Handbook, and it shows you basically there's unconsolidated material, which is the sands and gravels, clays and silts that are at the surface versus the rock material that's down further in the ground in most places. A lot of the country, rock is at the surface as well, but it's fractured, and so the type of material you have can make your porosity vary quite a bit. In sand and gravel, well-sorted sand has much more porosity in general than a poorly sorted sand, although it doesn't quite look like that on this figure. There's a lot more blue, but what happens is when you have multiple grain sizes, the small grains end up filling in between the larger grains and taking away a little of the porosity. So usually a well-sorted sand has a higher porosity than a poorly sorted sand. And when you get into fractured rock or limestone, limestone, for instance, those are usually caverns. There's also fractures as well, but karst topography, if you've heard that term before, is basically cave topography. And, in southern Illinois and Kentucky, Mammoth Cave, all those things were formed in limestone by the movement of water dissolving rock and creating those caverns. Dolomite, which is another common aquifer, bedrock aquifer, is more of a fractured rock, and what really matters when you're talking about a bedrock system is both the number and size of fractures and how well connected they are. You could have a well that just misses most of the major fractures, and you only can pump 1 to 2 gallons a minute, where if you moved over 200 feet and hit a major fracture, you might be able to pump 1,000 gallons a minute. And so it's it can be hit or miss in that regard, and there's a water there. It's just a matter of being able to connect to where the water is being stored. Okay, so the other important characteristic is permeability. And so an unconsolidated material, which again are sand, silt, clays that are sitting on top of bedrock, and in the northern half of the country, that's usually been deposited by glacial events. So glacier came along, it's 1,000 foot high and it scrapes up a lot of material 1 million years ago, for instance, and as it melts, it deposits sand and gravel first because they're the heaviest particles, and then later clays and silts, and that becomes the new soil surface. And so like in Illinois, in the glaciated part of Illinois, there are areas where there's 2 or 3 different sand and gravel aquifers that were deposited as a result of glaciation. And I know in the majority of the country that's not the case. You're on bedrock aquifers because there's not much other material. Other types of unconsolidated deposits, loess, windblown sand, some of those things also can provide water for wells. But permeability is basically a measure of how easy water can flow through that material. So gravel with large pore spaces, water can flow right through it. If you hold some sand in a jar and pour water through it, it goes right through, versus when you get down to the size of a clay particle, which is very tiny, and it causes the water to have to flow around all those small particles. Clay may have a lot of porosity. It may have a lot of water holding capacity, but because the particles are so small, the water molecules can't move through it very fast. And so in general, clays and unconsolidated deposits and shales, especially in consolidated rock, are considered aquatards, or confining layers, and they basically retard water flow rather than promote it or allow it to happen. So and as far as limestone goes and other types of rock, again, it's usually the number of fractures and solution cavities that you have. Sandstone's kind of a different example. It's basically consolidated sand that's because of the weight of the earth on top of it has caused cementing of the material. But there is a secondary porosity there that allows some permeability in the sandstone. Okay, here's just another example. If you had these aquifer units, sand and gravel versus dolomite, which is where water flows through the cracks in the rock, versus sandstone and dolomite and crystalline bedrock, which is usually very deep, and so it's not as fractured. This is kind of a diagram that shows how the water would seep into it if they were dry. Now, these units aren't dry. This is where the water is being held in each. But in a sand and gravel aquifer, water can just flow through all the sand and gravel grains. In a dolomite aquifer, you have water flowing through these preferential flow paths, which are the fissures and fractures that are in the dolomite. And as water moves through these, they dissolve the minerals and dissolve some of the rock and create caverns and that sort of thing. The one below that, the sandstone and dolomite, in reality, the geology you have at any location is multiple layers. So you have shales and sandstone and dolomite and limestone until you get to, I believe the right term is a crystalline basement, which is the crystalline rock that's below all the sedimentary rocks. When you get down to the crystalline basement or excuse me, crystalline bedrock, it's not very fractured. It doesn't have any secondary porosity, and if you're unfortunate enough to be in an area where crystalline bedrock is close to the surface, you probably have very low yielding well if you can use a well at all, or maybe you're using a dug and bored well in the unconsolidated material above it. This diagram was in the week 1 lesson, and it's from Iowa Department of Natural Resources. It really shows, it's a great cross-section that shows all the characteristics for basic groundwater flow. You know, shales are considered confining layers. Limestone and sandstone are considered aquifers in most cases, as long as they're fractured and have enough secondary porosity. And so when you have wells and the glacial drift at the top, again, if you're in an area that's unglaciated, you may have limestone close to the surface, or there may be loess or blown sand, some of those things near the surface instead. So you can have shallow wells that tap into these thin sands near the surface, or maybe you're in a well that's deeper that has more capacity. But I know we have in Illinois, in the Chicago area, for instance, there are shallow sand and gravel wells in sand and gravel aquifers that you can tap for water supply, but the larger communities up there are actually drilling down 1,600 feet into a sandstone limestone aquifer, the Mount Simon, for their large water supply because of the amount of water it'll provide. So, okay. And if I haven't mentioned it, you know, an aquifer is the geologic unit that will yield enough water to a well, and an aquitard, or a confining layer, is a geologic unit that, even though it may have water in it, doesn't allow water to flow readily to a well when you pump it. And so those usually limit flow versus an aquifer that, you know, allows flow to a well. Okay, there are two types of aquifers. You can have an unconfined aquifer or a confined aquifer. When water seeps into the ground, it infiltrates down to the water table, which is the upper surface of the zone of saturation, or where all the pore spaces are full of water below that point. And so if let's say you're in the water table is at 12 or 15 feet below land surface, and the aquifer comes up to maybe 5 or 6 feet below land surface. So part of the aquifer is dry, or only is partially saturated, and the water table starts at, again, 15 feet. That's considered a confined aquifer because it has a free surface. It has a water surface, so to speak, that's open to the atmosphere. And so at that point, the pressure on the water system is atmospheric pressure. In a confined aquifer, like in the last picture that I showed, that's separated by confining layers usually, it can be under pressure because the geology isn't level. It and excuse me. There can be pressure from another part of the aquifer that's pushing water, and so that the water level would be above the well if you put a well, or above the top of the aquifer if you put a well in it. And so those are called artesian because they're under a pressure that's greater than atmospheric. Okay, so here's kind of a flow diagram that hopefully ties all this together. So on the right, or on the left at the top, you have the blown sand and loess at the surface, and the aquitard below that is a clay. All of that sitting on top of the middle aquifer that says it's confined, that, you know, it looks like bricks. That's the limestone. And below the limestone is an aquitard that's probably a shale, and below that is a sandstone, the lower aquifer that's also confined, that has water flowing in a totally different direction. So in a groundwater system, it's part of the hydrologic cycle. So when water infiltrates into the ground and reaches the water table, then it can take a tenuous path to get back to the surface. It can be a few days if it happens to infiltrate in the ground close to a seep or near a stream, to millennia, as it says in the diagram, where some of that water from the surface will eventually work its way down through the aquitard, through the sand, through the limestone, through the second aquitard, and make its way into the sandstone at the bottom. And in this example, water's flowing to the left. Somewhere further away, that sandstone aquifer will discharge to the surface or to a shallower aquifer. What do you need? sorry. Hang on one second here. We have a question I need to deal with.
Yes. Someone would like you to explain a seep.
Okay. So someone asked about a seep. A seep and a spring are kind of the same thing, except a spring is usually in rock, and a seep is unconsolidated material. When you look at this diagram, the water table, which is a saturated surface, is here, and just because of the way the water pressure is, water flows and reaches the surface and causes a seep to form. You know, a lot of wetlands, that's what they are. They're where groundwater seeps up into the surface and causes, you know, there's a lot of different plants and all kinds of things that grow there. It's because it has a continual groundwater source full of minerals that provide water. And so I guess that's the best explanation I've got there for you know, what a seep is. And a spring, you know, there are places where in karst topography again, which where limestone outcrops to the surface, where folks use those springs for their water supply. I know down in Kentucky, there's I have a friend who they have a home that was built in the 1800s, and they actually have the spring running through their house, and that's how they use, that's their water supply. So those it's all based on topography and the way the glaciers, if there were glaciers in those areas, molded the topography, or and those sorts of things. But yeah, those are basically areas where groundwater comes to the surface. Okay. Okay, this is another example of a multiple layer system. The water table aquifer here is this whole unit. The solid line is a water level in the water table aquifer. And so this is a water table well. It's got a screen that's in the water table. And so the water level in the well is here. In this artesian aquifer, which is a deeper aquifer, it's confined. You have a confining bed above and below, and it's under pressure. And I mentioned in the last slide how much further to the left it might discharge. Well, the reason it's flowing to the left is because there's a higher area close to the surface where this aquifer is being recharged. This could be 100 miles away or 2 miles away. Usually these systems, depending on how deep they are, they extend over a long distance, and a lot of these rock formations go for, you know, thousands of miles. And so in this example, there's recharge to the deep aquifer here in this location, and that causes the water level in this material to be this dotted line. And the pressure put on the system by the water here forces water in a well over here to come up to that elevation. You know, a good example would be if I had a garden hose laying on the ground, and I mentioned this in the lesson, if there's water in it and you lift up one end, water comes out the other end. If you lift up both ends, you know, you can kind of regulate how much water's in your hose by how high you lift it. And once you have water higher than the top end of the other hose, it'll come out, which is kind of the same thing what a flowing well, artesian well is. And so here, this is the water level, the water pressure level. It's called the piezometric level in the deep aquifer. And when you put a well in this deep aquifer, like here's the screen for this, the way they've drawn this, it forces water to come up to this potentiometric surface level. It's the pressure caused by the recharge area over here on the system. And if your well's low enough, it'll start flowing. And there are many areas in the country where there are flowing wells. I know there are areas where the water level is close to the surface naturally, but maybe not flowing. A large recharge event, a flooding event in one part, you know, in this area might cause a well to flow for a week or so. And in other areas, you know, the land surface is high enough that the water level stays in the well, but it's well above the top of the aquifer. So in this case, here's the top of the artesian aquifer, the line that you guys can see this, right? Yeah. And so the water level's higher, which means it's under pressure, which makes it artesian, and that's the example here. Okay, so when you pump a well, there's two pictures here. As far as if you're looking in cross-section, here's your well, and you're pumping water out of it. This is a sand and gravel aquifer with a screen, and here's the water table. So when you start pumping your well, you draw down the water level in the well, and water surrounding the surrounding aquifer, because it is trying to flow downhill and the water pressure is higher further away, starts flowing into your well. And your porosity and permeability dictate how fast that happens, so how much drawdown you might have in your well. In this example, it's kind of an ideal system, but this shows elevation lines at the bottom. So when you're pumping your well, the static water level is 460 feet mean sea level. And when you pump your well, you drop the water level down to 400. And so you have these concentric lines of equal elevation of the water table surface that have occurred because of this cone of depression. And so why this is important is in some locations, if the porosity is low or the aquifer is not very thick, you can draw down this quickly and cause a cone of depression that's very large. In other areas, it may be very small. You might even be able to notice it pumping at a low rate that you might for a domestic well. And so, but that's the concept here. And so as we move forward, if there's another well close by that's in the same cone of depression, all of a sudden you start seeing more drawdown, the water level surface is lowered, and I know we got a question the other day via email about a rural landowner who has a well that all of a sudden their well went dry, or at least their pump went dry, and what's happened is the area has been developed, and now where there were 20 or 30 wells in a square mile, right near them there's a subdivision with another 100 wells, and you have all those additional people pumping, and so it's keeping the water table lower, or the aquifer level lower than it had been in the past. Okay, so well type matters. We're going to go into the different well types here. The bottom line is the geology of your area and the type of aquifer you have will dictate what your well type is. In some areas, like the southern third of Illinois, which is where my experience is, there is no real aquifer available. It's below the area that was glaciated, so there's no sand and gravel aquifers near the surface. And in that area, all the bedrock aquifers are saltwater. They're as in ocean saltwater, and so they're not really potable and available for supply. So in areas like that, or where there just is no real large source of water available, dug or bored wells are installed, and they are as these large diameter wells that are meant to be storage basins for water to seep in near the surface. And I'll show an example of that in a minute. Another type are drilled or driven wells, sand and gravel, in a sand and gravel aquifer. Yes, hang on one second.
We're having some audio difficulties with Steve, and so we're going to ask you, Steve, to go ahead and unplug and replug your microphone back in, and maybe that can resolve the issue. Yeah.
So no one, okay, I'm going to unplug my mic.
So it's kind of coming in and out.
Hang on one second. Okay. Does that resolve the issue? Did that help at all? Apparently some folks are having trouble hearing me. Okay, well, we're going to keep moving. If everything is, for those of you that are having trouble, if it's better, yeah, let us know. Thanks. Okay, so in a sand and gravel aquifer, you can have two types of wells, really. A drilled well, which uses a screen, or a driven well, which is a shallow, called a sand point well in some cases, where you just drive it into the ground literally to reach the saturated part of the sand and gravel unit. And I'll talk about each of those here in a second. Also, in rock wells, they're usually drilled. Now, a couple people have asked about Well, someone asked about the cable method for, I assume they mean the cable tool method for drilling. I'm probably not going to talk about that today, but we'll have that information available. And a really good source for the different types of drill rigs and how those work is on the National Groundwater Association's website. And we'll have a link to that, or I'll make sure we do on our website so you can find that information. So, in some cases you may have choices. You know, the example we showed, there was some sand and gravel at the surface, there was some limestone separated by some shales, and then some sandstone and more limestone. Each of those can have a different water quality, and in general, your state, either Department of Natural Resources or your health department or State Geological Survey will know, you know, this aquifer has high iron, or, you know, different choices you might have, but most of us aren't that lucky. A lot of times there may only be one aquifer that provides enough water for a well, and so you're kind of stuck with, once you know the geology of the area, you'll be able to pick, to determine what kind of well you want to drill. And a good example of that is, I know in Wisconsin there is a bedrock unit that's very high in arsenic, and they've actually legislated now that new wells can't have to close off that unit if they drill through it, or they need to be they need to make sure that water's not coming from that particular unit, and so it can be an issue. You should have a log and know where your water might be coming from. If you don't have a log, you should ask your driller if you know who that is. I know one of the biggest problems with drinking water wells, especially in rural areas, is they're old. The driller may not be around anymore. You maybe weren't the original landowner. The well's always been fine, so you may not have some of that information. We did discuss what to do about that in the first lesson, and really you need to contact your state agency that might have that log. And if it turns out you don't have a log, the best thing to probably do is contact a driller, a local driller, and have them try to find out your depth for you and some of those things so that you at least know where your water is coming from. Are we good? All right. So as far as bored wells go, they're large diameter, and again, this is a bored rig, this photo, and you can see those guys down in the back there, how big of a hole. That's a 4-foot diameter hole they're drilling. This is a place where you can see the soil. It's certainly not sand at the surface. They're probably, it's glacial till, which is mostly made up of clay and silt and some intermixed sands. A lot of times those units in glacial areas have very thin, I'd call them sand stringers, maybe 6 inches of sand separated, you know, with 30 feet of clay on each side. And those small sand units will hold water and allow water to move to the well. And so you put in a bored well, which is large diameter and maybe up to 60, 80 feet deep, and that acts as a storage basin. So those little seeps can continually resupply your well and keep enough volume there to supply you for the day. And then they will continue to seep in, and it's just, there is no sand and gravel unit, or there's no bedrock in that area that has potable water for you to put in a well, a drilled well, where you'd have a screen. And so this is your choice, basically. And you know, the whole southern third of Illinois is that way. I know there's other areas across the country that are the same. And it's just, you know, it's the way the geology is and what you have. So here is a diagram that shows two properly constructed, point that out, bored wells. And the other issue with bored and dug wells I forgot to mention is a lot of old wells are hand dug wells. I grew up on one. My grandpa dug our well back in the 60s. It's 14 feet deep. It's got uncemented brick that make up the casing, so to speak, and it's got a small well house over top of it, but it's in a ravine where there's a cornfield on one side that slopes down to it, and there's a cattle pasture on the other. And so it's not necessarily the best situation, and I don't believe it's being used anymore. But a properly constructed bored well, you can see from the figure here, there's a lot of fine textured soil, clays and silts mostly, maybe with a little sand. And then there's these thin sand lenses where water may be able to seep from the clays and get into the well. So you either construct it to the surface with this 3 or 4 foot, this is a 3-foot example, casing, and then have a proper seal on the surface. Or in Illinois, they've changed the law now because of the potential for contamination of these shallower wells. The Illinois Department of Public Health requires you to have 10 feet of fill with a regular monitor cap that you'd have for a drilled well over top of where the well can take in water. So this is all clean earth fill material, so that it protects it at the surface, and surface contaminants can't move down through here, and your water bearing area is down in the lower half. So here are 3 wells. It says bored wells here, but this is not a bored well. It's a hand dug well. This particular well I got from Virginia Cooperative Extension's, one of their bulletins, but it's from Brian Swistock from Penn State. And these 2 I took pictures of from some work we did looking at shallow dug and bored wells and ag chemicals. Now this is an example that I just showed where you have a normal monitor, red monitor cap, 4-inch casing, or this is a 6-inch casing that goes down, and 10 or 15 feet down the large diameter well starts. This is an example of a hand dug well that has been here since the 30s. There's the electric outlet for it. There's a water line that runs back to the house. This is a cattle pasture. This is a cornfield. And they've got boards and tin with cement blocks on top of it to protect it at the surface. There's insect issues. There's, runoff issues if there were a huge rainfall event. And ironically, as far as ag chemicals go, this well, we sampled it 8 times, I believe, over the course of a year, and it never had elevated nitrate or any kind of pesticide detection, where this well did. And so having this situation doesn't always spell disaster, but it's certainly much more of a risk, and it's something that we recommend they would correct and probably put in a different well. So there are a lot of these in rural areas of the country because the farmsteads in those areas have been there since the 1800s, and so the well still works, and it's always been great tasting water, and you've heard all those things. Like I said, I grew up on one of those too, and it's still certainly a health risk, and I wouldn't certainly let my children drink from it. Okay, so sand and gravel wells. Here's a screen, a well screen, and so the way that works is there's tiny slots in the screen. It's woven, kind of like a screen on your door, but much smaller openings so that water can pass through, but the sand that's in the formation can't. And if you have a sand and gravel well and you're pumping sand, it either means that there's some kind of breach in the screen, or whenever you install this well, let's say this is a 6-inch casing, you may drill a 12-inch hole and you put gravel pack around that screen, which is larger particles, so that it'll help keep the fines out, and there may be a problem with your gravel pack having a breach in it. So, and usually the driller will size your screen based on the sand that they pull out of the formation when they drill the well, and so that way or they know what size screen to use to make sure that you can get enough water and also keep sand out. So, and this is a typical installation. You have a screen at the bottom, and usually a submersible pump if it's deep enough. That's on a drop pipe that can be pulled out. A pitless unit, which is you put in a pitless adapter so that this is a water line running to your house, so it's below the frost line. So the idea is by having a pitless adapter, you don't need a well pit. And there are a lot of older wells that are still in pits, and I'll show an example in a minute. But if you do have a well that's in a pit, there's a lot of risk there. Water standing in the pit can eventually lead to flow around the casing and start working its way down as it dissolves some of the soil material. Not being above the surface makes it prone to flooding if there's such an event. which can cause electrical problems or cause contamination problems. And so well pits are just, they need to be eliminated. This is a sand point or driven well. When you're in an area where the aquifer is close to the surface, sometimes you can push in a screen and get your water that way. There are areas in all over the country where it's near a river and it's sandy where you can do this. The thing you need to remember is when you don't have much topsoil and it's sand at the surface, anything from the surface can infiltrate into the water table and eventually get in your well when you start pumping it. What we recommend to folks who have shallow sand points is use them for your garden or other things. Don't use them for your drinking water supply. If your aquifer, your shallow aquifer, is say 50 feet thick, you're much better off putting in a drilled well with a screen near the bottom. It's more protected. Sand's a natural filter. The more sand that water has to travel through to get to your well, the more it's likely to filter out, especially bacteria and organisms and things that might come from the surface. So again, they're very susceptible for pollution, and I know every state's different, but in Illinois, you can put in your own well, which I don't recommend. You should always use a licensed contractor, but hang on one second. But if you are going to put in a well, you know, I don't recommend using putting in a shallow sand point well. Okay. Someone asked about a well log? No? Okay, we're good. We'll get to that in a minute. So a bedrock well is basically the same type of drilled well as a sand and gravel well, except you don't have a screen at the bottom. And the reason is, you know, bedrock is solid. As you drill through it, you might encounter a fracture or two, but you don't put casing all the way down to the bottom of the well. You put a steel casing in generally, and you seat it somewhere in the rock so that it's solid. But then the rest of the, from this point on, this is an open hole. And that allows all the fractures to be connected directly to your well, and so water can flow through those fractures when you start pumping your well and replenish your supply. And so the deal with fractured rock is you may have fractures that run typically in certain directions. And so when you pump your well, you may be pulling water from the north from a half mile away eventually, where from the west and east you're not getting water from more than, you know, a few feet away because there are no fractures running in that direction, and water is going to flow with a path of least resistance, and an open fracture obviously is just allows water to flow freely through it. So another example of both a sand and gravel well and a rock well. Here we have fine sand, so we put a screen in, and there is a gravel pack, or these larger particles to keep the sand out. Around the well, the hole you originally drilled was larger, a few inches larger, so that you can put this pipe in. You grout this, and you put a sanitary seal on top. And the slurry, this clay slurry they mentioned, is mostly clay or bentonite or sometimes cement, so that it protects around your well from, because you've disturbed the soil, you're protecting from surface infiltration. And the same way with a drilled well in bedrock, you put a grout seal to protect the surface from any infiltration near your well, and it's seated in the rock. Here's some shale that they've seated this casing in, and then you have these sandstone and limestone or dolomite lenses with an open borehole that allow water to freely flow into your well. Okay, so this is, I think we're getting to the end here. This is a typical setup for a water system. You have your well, and you have a pitless adapter that's, again, your pitless unit is the area that for your discharge pipe to run into your house, and it's below the frost line. I know in some parts of the country you don't have a frost line, but that's why a pitless was developed, so that if you need to do any maintenance on your well or any other work, your pump and the pipe that connects your pump are all accessible from the surface. It eliminates the need to have a well pit, which here's a picture from I believe this is from a Pennsylvania publication. I didn't put a source here. I apologize. Of a well in a pit. You have a large rainfall event. This looks like this was a hand-dug originally, maybe well, that they put a drilled well inside it and filled it in. This is susceptible to flooding, all those sorts of things. And so it's much better just to extend this pipe to the surface, fill this in, and provide a safe, around your well installation. And so there's things that are recommended for your well. Have your well 8 to 12 inches above land surface. Usually they recommend you mound dirt up near your well so water always flows away. You have your pitless unit here that runs your discharge water into your house into a pressure tank. And you have your pressure switch is hooked to to allow when the pressure gets to a certain point low, it kicks on your compressor to make sure your tank's full. Your pressure tank has a bladder in it generally. It's meant to keep this water under pressure, so when you turn on your faucet, you have flow into your faucet. And so you can think of it like it's your own little internal water tower, so to speak, but it uses pressure instead of height to cause that water flow into your faucet or well. The other thing about a pressure tank that's important is they're sized based on your need. If you had a very small pressure tank and you used a lot of water, your pump would have to kick on frequently. Excuse me? Okay, hang on one second. We have Cassia needs to go ahead.
We have someone who asked, on this graphic it shows 12 inches from tap to ground, but on one of the early slides it shows 6 inches. Why?
That's a very good question. And again, if you've noticed, what I've tried to do with this, and with this class, and you'll notice as you go through it, we're trying to use resources from all over the country to help folks get an idea of where they might be able to find help locally, for one thing. And so different organizations have different recommendations as a bottom line. I said 8 to 12 when I mentioned it because I think what we tell people is at least 8 inches above the ground. And the idea just being that you need to have it high enough so that if there were even, you had a rainfall event that, 3 inches or 2 inches in an hour and it caused some local flooding in your yard, that it didn't overtop your well. And so, higher is better, the bottom line. And it's a safety precaution so that it can protect the surface from affecting your well. And so, when I said I didn't catch that, but using information from different sources, sometimes there's going to be little disparities in how what they tell well owners. Just like in a later lesson, we'll talk about something that I learned since starting this project. You should never put Clorox if you're going to chlorinate your well. A lot of even local health districts and things like that recommend pouring Clorox a certain amount down your well. Well, the folks at Minnesota Department of Health pointed out that pouring straight Clorox, because it's so concentrated, can actually harm some of the seals for your pitless adapter. And really what you should do is you should mix your Clorox with water to a certain, to lower the overall concentration to a few hundred ppm versus 5% or whatever it is in straight chlorine, so that doesn't happen. And that'll be one of the things that we recommend later when we get to that lesson. And so there are differences around the country, just like the diagram for the sand point was from a co-op extension office that basically gave you directions for installing a sand point. We would never recommend anyone install a sand point just because of the vulnerability of the surface. A lot of times you're in a rural area, it's agricultural, and it's pretty clear that there's more risk, not necessarily there's more contamination, but there is more risk of contamination closer to the surface and whenever there's not a lot of surface protection for things that can infiltrate into the aquifer. So, but that's a very good question. And we probably need to come up with the best practices. This is, I use this. This is from Minnesota, I believe, as well, which I think it's being cut off here for some reason. But it's a very good diagram that shows, a typical system. And it's simple. It shows you what you need to know. And this is part of Lesson 4, and there'll be a lot more information about differences in pumps. And, there's jet pumps and there's submersible pumps. If your water level is fairly shallow, you don't have to have a submersible pump. There are areas where people don't have a pump because their wells flow. So there's all kinds of differences that you can find around the country. And, in this webinar, we're already going on an hour. So, again, this is meant to show a few different things than what are in the class lessons. But the main point of this was questions, so I think we'll try to get to those. Okay. All right. So one of the things I wanted to mention, ironically, I've used a lot of sources to come up with this information. There's so much information out there, and some of it does conflict, but most of it's very useful, and if you just need to know where to look. And so the idea behind this class is not to reinvent the wheel or create a bunch of new information, but we're trying to use all those sources that already exist that you may not be aware of and put them all in one place so that you can find the information you need. So that's what our focus is for this class. And so you'll see as you go through the lessons that are emailed to you, things from a lot of different sources. And those that do it best are what we're trying to use. And so, and eventually, I don't have it on there now, but eventually all the sources I use for this talk today, they will be on our website. So, the questions I have we need to deal with are, one, are you receiving the class materials? We've had a number of folks who have emailed us and said, hey, I thought I was going to get your class starting this date. It didn't happen. We certainly want anyone who has signed up and hasn't received anything to let us know. We have an email address, info@privatewellclass.org, and you can also ask us questions there. We may not get to them right away. In total honesty, this class has taken off a lot quicker and than what I ever expected. We have almost 1,100 people who now have signed up for the class, and so we've received a lot of questions. And it's going to take us a little time to get through those and kind of group them so that we aren't answering the same question 4 or 5 times. And that's why we will, the questions we don't get to today that you've asked on the webinar, eventually will go in this FAQ or frequently asked questions section to provide answers for folks. And as I said at the beginning, there's some of these questions I can't answer. I don't have the expertise, but hopefully I do know the right folks who can, and so that's what we'll do. There are 2 other webinars, as I had shown in the beginning, and so we will make sure, if you haven't signed up for those, if you're interested, and as you go through the class material, anytime there's a question, just ask. So, okay.